Okay, the purpose of this video is to take a look at trig graphs and specifically look at the transformations that come from each one of those. We've looked at transformations before from lots of different perspectives. Here's the trig one, but just to remind you, we did stuff like this back in other sections. Is that right? No. Well, it's like, I guess it's like that. Y equals a bx minus c squared plus d, something like that. And there were specific things that each one of those letters did to transform the graph of a particular function. So similarly, when we look at trig graphs, which look really cool, trig graphs, there'll be similar transformations. So again, we can plug things in the A slot or the B slot or a C slot or a D slot, and we need to be able to determine what the effect of each one of those transformations are. So in the end, at the end of this section, you'd want to take a look at this function or this equation and determine what the graph of that would look like, or at least what would be the effect of each one of those letters. Okay, so in the textbook, they might give you some equations that look like this, where this is our normal one, but then they've revised it to look like this. And I don't mind this revision. It looks a bit more complicated, but it clarifies something about what happens with the value of c. Typically, that was our left-right movement, and writing the equation like this clarifies it for us. So we'll see that here as we look through some. So why don't we just try each of those letters, A, B, C, D, and see what happens with each one of them. So I have a handy dandy graph here somewhere, right there. Okay. So what I've done here is I just have the graph for y equals sine x. So there's sine x. Notice it's a repeater kind of thing. It's a pretty kind of one. And if you put a bunch on there, it might look quite pretty. Anyway, that is the graph that we're currently looking at. And what I want to do is I'll create another graph, create a new equation, and let's call this one 2 sine x. Whoops, not s, but x. There. Okay, so compare the two graphs. The one that's highlighted here is the one that's darker. So when you take a look at the graph, what is happening? And sure enough, just like our other one, I think we called that vertical translation, but it looks like it's doubling all the y values. So this is the normal one, and this is the one that I just plotted, and it's doubling all the y values. So just maybe to follow that, what if I put a 0.5 there? That probably will make it skinnier. Sure enough, puts it skinnier. What if I put a 10 there? Oh, way taller, you can't even see it. How about a 3? Yeah, a 3 one looks pretty. This is sort of fun. How about a minus number? What do you think is going to happen if you put a minus in there? Say a minus 2. Oh, so it does two things. It flips it over and it doubles the height of it. When we're looking at a trig graph, typically we have a different name for that because it's sort of a periodic function. Rather than calling it like a vertical translation, we actually give it a name for it, and that's an amplitude. So in this case here, the graph, rather than starting here and going like that, it went down. That's because of the negative sign. And it went double as high as this one, or another word is amplitude. So its amplitude is double the amplitude of that graph. Let's just capture that sort of right here in this slide. So A affects amplitude. So it affects the amplitude, and just like we saw on that graph. The other thing that it does is it also can reflect the graph on the x-axis. Okay, again, A, just like it did with the other transformation, it has a major effect on the y values of the graph. Okay, let's go on to another one. Oh, D, I'm going right to the end. Okay, let's try something with D. And remember, D was this one. So y equals sine, it has a bunch of other letters, x plus d. It's the one at the end, sort of on its own. So it's not in brackets, that would be a C guy in here. It's the one outside right at the end. Okay, Let's go back to our graph and play with some of those. Okay, so I had a -2 there. Let's just take that back just a sign. So now I've got the same graph just on top of each other. But let's put a number there. So let's put, say, +1. What are you betting it's going to do? Sure enough, moves it up 1. What if I put a 2 there? Uh-oh, can't even see it. But it'll be, we better go up so we can see it. Oh, I put +12. Oh, that's why. 12. There it is, way up there. Okay, let's get back. I didn't want 12. 2. There, that's better. Put a minus sign. -2. Flips down to the bottom. You get the idea with D? Not a whole lot of trouble. So D, again, it affects Y values, and it just translates the graph. Sorry for my writing, either up or down, depending on the sign. It goes up if it's positive. It goes down if D is negative. Okay, good. So that's A and D done. Now which one? B. Okay, B, one of my favorites. Let's go back and play with B. Oh, just to remind where B is, Y equals sine, and it'd be the thing right in front of the X, so like BX. So it'd be a number in brackets maybe, but it's being multiplied by the X. This one has effect on X values. Okay, let's go try one. Okay, so let's lose this -2, and I want to put one, not there, but one right there. So this is our normal graph right there. What if I put a 2 there? 2. Ooh, that looks pretty. Now let's just see what happens there. There's a 2, and what it seems to be doing is it shrunk it, right? A vertical, not a vertical, a horizontal accordion kind of look. But let's see if that number 2 makes, has a bearing on it. If you look at the normal graph, this one here, it finishes at one whole cycle, and in a minute we'll call it a period. It finishes that period in a matter of 2 pi, or 360 degrees. And how about this next one? This one that we just did finishes once, twice. So it finishes it in 2 pi. It does its same period twice. Okay, let's try a different number. How about if I put a 3 there? Will that follow? Are there 3 periods? There's 1, 2, 3. So there's 3 periods that it does in a matter of 2 pi. Now, but how much would each one of the periods be? So it goes up, down, right to there. It finishes a period. So maybe that might be an interesting thing for us to know, is how long does it take to finish one period? Well, each one of these things are 30 degrees. So this would be 30, 60, 90, 120. So this graph finishes one period, or its period would be 120 degrees. And I'll show you in a sec just a quick little formula to help you indicate that. What happens if I put 10 there? Well, that's a ton of them. How about 0.5? Oh, now it's lazier, eh? So it only completes half a period in 2 pi. It would take 4 pi to finish the whole period. How about, what if I did a negative number? -2. Oh, something funny happened there. It's still complete in a period twice in 2 pi, but this time it's upside down. This one starts going up this way, but this one starts going downways. What do you think that minus did to the graph? Hopefully you're saying, well, it reflected it on the y-axis. So rather than starting and going this way, it's actually starting and going this way. So that negative in front of the b value reflects on the y-axis, and the 2, of course, makes it double, or it makes its period, so there's 2 of them finished in a matter of 2 pi. Let's sort of put that down here. So B, what does B do? So the first thing is that it affects the period of the graph. Period. Period of the graph. Okay? So, and to determine what the period is, so the period isn't equal to B. You can't just say, well, the B's period. But the period of the graph, how long it takes to repeat itself, is equal to 2 pi divided by whatever b is. So when we put a 2 in, like for b, we'd have something 2 pi divided by 2. These cancel out. So the period of the graph would be pi, or 180 degrees. Let's just go back and confirm that. So if I put a 2 here, so the graph goes up and down and up, so 1 period in pi. Okay, the other thing that b did was that it reflects, if it's negative, we should say a negative b, reflects on the y-axis. So that's the two things that it does. Okay, so that's perfect. So now let's look at c. So c is, I guess just a review, is y equals sine, and this will be x minus something, so say pi. So that thing right there is my c value. Let's see what happens graphically with a trig graph when I change the c value. Okay, so I want to lose that one. So there's just our normal graph again, but now I want to put something in right there. So let's say a minus, and let's use pi notation. So why don't we say minus pi over 2. Okay, just take a look at that. So what happened to the graph? This one that I just changed, this transformation, is the darker one. So it looks like instead of starting here, it started over a bit. And it looks like it's the same graph, it's just taken the whole thing and moved it. And which way did it move it? It usually starts here, this time it's starting there. And so it moved it to the right. So with a minus sign in there, it means it moves it to the right. And pi over 2 is 90 degrees. 90 degrees is right there. Yeah, so it moved the graph right 90 degrees. Okay, let's try another one. What about minus pi? So that would mean that it takes the whole thing and moves it over pi. Yeah, sure enough. So rather than starting here, well, that's a pretty graph. Rather than starting here, it moved the whole thing over, and now it's starting there. What if I put a plus in there? Oh, it's sort of the same thing. But the plus would mean rather than moving it this way, it would move it that way. Maybe I should have put pi over 2 divided by 6 or something. There. So it took the whole thing, instead of starting here, it moved it over left. Pi over 6 is 30 degrees, so it moved it left 30 degrees. Now, I want to see what would happen. Well, let's go back and just say something about that c. So c is a horizontal translation. Horizontal translation, left to right. So if it's the value that's in there, if I have x minus 2, for example, in there, sine x minus 2, this thing here is going to move right 2. If it was sine x plus 2, it would move left 2, or whatever that number is in there. I guess I'm a little bit careful with the sign there, because I don't want to say that this is minus c, because the general formula has a minus in there. So really, this one here is a minus c. If I put a minus, I don't know if I'm explaining that right. If it's x minus c, that's sort of the general formula of the thing. Then in order to get a positive there, it has to be x minus a negative c. And that cancels each other out. So really, this one here is a positive c, and this one here is a negative c. But that might be too hard to remember, so don't worry about that. Just remember that if there's a minus sign in there, it's going right. If there's a plus, it's going left. Okay, the other thing I wanted to show is the interaction between two things, and that's the b value and the c value. Let's take this one back, and let's just call it a pi. So that has moved the thing over to the right by pi. But watch what happens when I put a number in here, right for the b value. If I put a 2 in there, usually we said b affects the period, right? So the period now will be, instead of taking 360 degrees to repeat, it'll repeat itself in pi, or 180 degrees. But watch what that also does to how far it moves it. Okay, so in this one here, when I see a pi there, I'm thinking, well, that moved it right pi. But if you take a look at this graph didn't move it all the way to the pi. It only moved it halfway. Yes, the period is now double, right? Or not double, but it's half. The period's now 180 degrees, not 360. But also, let me go back to this one. Take a look at how much it's been shifted to the right. That's what this value does, right? See? So it moved it, oh, this positive would move it left. So it moved it left by pi. And so now my start, usually my start is start here and go up. This one now is a start here and go up. And I moved it to the right pi. But as soon as I put a 2 there, notice that it halved that distance. So when we're looking at what the horizontal translation is, I can get this idea if it moves right or left, whatever that number is. But if there's a value in front of b, properly I should say that the horizontal translation, or another name that we use for that, is the phase shift. The phase shift is equal to whatever c is divided by b. And in that big formula that I showed you right off the bat, not that one, this one right here, that's why I like that there, is because the phase shift isn't just c, it's whatever c divided by b is. On many tests, a person might not give you a b value with a c value, so often you see ones like this, sine x minus 3, etc., and you just say, okay, it moves it right 3. But if I give you a question where it says sine 2x minus 3, then the phase shift isn't 3 right. The phase shift will be equal to 3 over 2 right. Okay, so you just have to be careful with that thing there. Now, all I've been doing so far is just looking at the sine graphs. So I haven't looked at any other types of graph, it's just been the sine graph. But if you were to take and do the cos graph, the exact same things apply. Let me just take you through that one of those quickly. So let's look at, oh, let me change this one. So this is a cos graph. So there's the normal cos graph. And this one, I'm going to get rid of all the stuff in there too. Just put an X. So there's the normal cos graph. Notice that the cos graph, rather than starting here and going up, that's the sine graph, the cos graph starts there. And since they're co-function functions, I guess it makes sense. When one is one number, another one is the opposite of that. Not opposite, but they work in tandem, I guess is what I'm trying to say. So this one starts here and goes down. Now let's put a number in front of the cos. If I put a 2 there, notice it doubles things. If I put a minus sign, it flips it over. So A does the same thing as normal. If I put a B value there, like a 2, it should make the period 2 of them into 360. Sure enough. If I put a minus 2, it'll reflect it on the y-axis, and it'll go this way instead. If I put a number over here, so minus, say, pi, so now it's moved the graph to the right by pi. So rather than starting here, it's now starting here and going down. And also if I put a number out at the end, plus 1, it moves the whole thing up or down. So the ABCDs for cos are exactly the same as sine. It's just that they are they're just shifted off a little bit. And that might be a good thing to note here is, whoops. If I have the cos graph right there, there's 2 cos graphs, but let me change one to be a sine. Whoops. So there's a sine graph, and so sine starts here, goes up, and this one there. But notice that if I were to take the sine graph and shift it over by 90 degrees, or pi over 2, it would be the same graph. So if I took the cos graph, okay, let's take the cos one and shift it to the right 90. So if I want to shift that one to the right 90, shifting to the right, I need to put a minus there. And 90 degrees, because I'm using the pi or radian notation, I've got to go pi divided by 2. Notice that now it's the exact same graph. So it's pretty tough if you were to see a graph to know whether it's a cos or a sine graph, because it could be either one shifted one way or the other. Often in the book they will give you the graph that is transformed the least, and that's sort of the default one to go with. But keep in mind that this graph could be the sine graph, or it could be the cos graph, just shifted over a little bit. All right, hopefully that gives you a good introduction to working with the trig graphs. Again, it's just a matter of identifying the transformations. That's the main thing you want to do. I might ask you to draw one that has a couple of transformations in it, but I won't ask you to draw one that has way too many transformations. Okay, hopefully that helps.